All right, the recording has started. Welcome everyone to our January SCARC club meeting. I'm excited for tonight's presentation. It's a topic that I think there's a fair amount of black magic and dark arts around, as Chuck can probably attest to here. But hopefully you can cast aside some spells and get us started there. Chuck does have a bit of an icebreaker here. I'm going to bring that up and share that here first. One moment while I do so. I got ahead of myself. We're going to share that window.
Just a demonstration of how you can listen to something very interesting when it's all done. What was that about? And it's how so many of us, approach lightning protection and grounding. So go ahead.
Senator Collins, thanks for coming in.
It's a great pleasure, thank you.
This ship that was involved in the incident off Western Australia this week.
Yeah, the one the front fell off.
That was an interview. There's two people talking. That was an interview about this ship where the front fell off. So it wasn't, but similar. Yeah. Actually, it turns out I did a little research on the guys doing this, and I mean, that is kind of what they do for a living. They've got all different kinds of topics. This is just the one I stumbled into, and it struck me because a whole lot of talking and it's kind of like what we're doing here, looking at the lightning protection. Okay, there we go. So what is grounding? If you notice on the first page here, this was called grounding originally. But it's really around lightning mitigation. And usually that has a lot to do with grounding, at least in our minds historically. Lightning mitigation and grounding go hand in hand. And what we're going to do here today is show that is true, but it's not the whole truth. And we're going to kind of change how we look at some of this. So we have electrical safety ground. We're not discussing that at all, even from the prospect of lightning. We have an RF ground, which contributes to the efficiency of your antennas. Very important for that. But it's also a means that we use to try to hold everything at the same voltage relationship. That's one of the purposes of a ground. So voltage differentials or voltage relationship, what are we talking about? That outlet right there, if I were to go over and measure the voltage, and let's say this were actually Earth, and I measured Earth to that outlet, it would show 110 ohms. The equipment that we have plugged into that is wanting to see 110 ohms, or 110 volts, wanting to see 110 volts. Okay? So let's say we have a ground fault or a lightning strike, and this floor, the ground we're standing on, goes to 1,000 volts. It's like, oh my God. Well, if that outlet goes to 1,110 volts, the equipment doesn't know the difference. It's still happy. It's not going to get hurt. So the whole thing about this is about voltage differentials and making sure that when lightning does strike, and it will, that everything rises together and falls together at the same time, not 100 milliseconds apart, but at the same time. And if everything rises and falls at the same time, nothing's going to get hurt. Now, this all started, I went to Polyphaser for a couple of weeks, took a class, and one of their big things is there's no limit to the amount of money you can spend for lightning mitigation. For that matter, while I was there, they had received a phone call. The instructor we had was called out of the room. Lo and behold, someone wanted to protect equipment on the Rock of Gibraltar. And they were told that if you can afford it, we can do it. You may not want to, because the Rock of Gibraltar will no longer look like it used to. Be a lot of copper sheeting and that type of thing. So, but they always warn, especially from a business perspective, pay attention. Do not exceed the value of what you're trying to protect. because replacing that stuff, not only do you get new equipment, but it's going to be cheaper than maintaining all of this. And all of this lightning protection, all it does is mitigates the effect of the lightning. You can never, ever prevent lightning from striking. That's just not going to happen. So the whole thing is to mitigate what happens. So it's all about voltage differentials. It's the killer of the equipment. We want to reduce that differential whenever we can and however possible. That's the goal. And reducing this differential prior to any protection, lightning protectors as we call them, reducing the differential prior to that point can only help. So what we're going to talk about is it's kind of more of a state of mind. The purpose of lightning mitigation is to, again, minimize the voltage differentials. And the mitigation is all about planning, anticipating what could happen. It's all about your state of mind when you are putting your station together. So I only needed 80 foot of coax, but I got 100 foot coming down the tower. What do I do with the excess? Well, I'm going to just coil it up at the bottom of the tower. No. There's all kinds of things like that that are that we don't think about. So it's all comes down to, in many respects, it's a state of mind. This is just a couple slides here of just technical stuff that really has nothing to do with what we're talking about other than it's interesting. And basically, the lightning strike, and I guess my big eye opener when I went into this, I was thinking a lightning strike is just a big surge of direct current. Well, yes, but that surge is so fast that there's all kinds of ringing involved with it, and hence it has the same impact as RF. And so if you start looking at your protection and your mitigation in terms of RF versus DC, in other words, DC resistance doesn't really matter. Low resistance path to ground doesn't really matter. What does matter is a low reactance path to ground. That's what matters. And we don't normally think that way when it comes to lightning. This is how a lightning, how it actually happens. It's stepped, and I'm sure you've probably all seen slow motion movies of that happening. The length of the step, it's very fast, but the length of the step can be, I guess that's on the next one. Yeah, the length of each step can be 150 foot. Takes about 50 microseconds. 1 microsecond of that is the actual jump, and 49 microsecond is the pause, getting ready for the next jump. And you have the two ends of the come together in the middle, and when that happens, that's when everything takes place. Because of this ringing and because of this RF-like characteristics, after it strikes, there's RF generator that RF energy that is re-radiated. There's magnetic fields that can induce current into adjacent structures, etc. So the thing is, we need to avoid anything that looks like inductance, the coils of the coax and that type of thing. So we just got to get our heads around the fact that eliminate inductance and eliminate reactance in the path of that energy that's coming down. The other thing is there's all kinds of energy in that lightning strike. So we have to dissipate it into the ground and spread it out as fast as we can away from what we are trying to protect. And it's a whole lot of energy. So if you have a single ground rod and then you think that's going to protect you, it's overwhelmed immediately. The earth is saturated, The ground, everything about it is saturated. You're not moving any current anymore. You're just letting it build up into the attached equipment and everything else that's getting fried. So dissipating the energy to Earth as quickly as possible becomes very important. So again, you have to keep thinking about RF. I'm not creating a good DC path to ground. That's not the point. I'm creating a good RF path to ground. And it seems like most of the calculations that they do around all of this is right around 10 meg. That seems to be the predominant frequency, if you will, of the RF component to this. So we're not going to really get into the science of it or the engineering of it. It's just more rules of thumb. What should you keep in mind? Always relate what you are doing to the RF, that is the high rise time pulses, removing inductive reactance, so in the form of coils, that type of thing. Avoid saturation of anything. So radials at the base of a tower for the purpose of lightning mitigation are a great resource and something we don't even think about. Thus, radials are part of an antenna. It's the RF ground on an antenna. We don't think of it ever as being part of lightning mitigation. And again, avoiding voltage differentials. We're going to talk a little bit about ground rods, grounding conductors, ground systems, coax, etc. First of all, in ground rods, any length over about 10 foot is wasted. For that matter, the way it was presented to us in the class, 10 foot is wasted. If you want to save yourself money, go buy a 10-foot ground rod and cut it in half. You're going to save money and you're going to create a better path for the energy to be dissipated. So multiple short rods tied together are better than fewer long rods. And multiple short rods should be tied together with nothing less than number 10 wire. But we're going to show some pictures where the radials coming out from a tower will actually have ground rods spaced out the radial, again, for maximum transfer of energy into the earth. That's what we're after here, maximum transfer of energy as it goes away from the tower, assuming the tower is what's been struck. I mean, everything we're talking about here, we use the term tower. You can change that for antenna if that's all you have without a tower, but still the tower sticks up in the air and becomes a good attractor of lightning. Hence, everything tends to be pointed that way. So grounding conductors, for example, again, think about RF, think about skin effect. Do not think about DC resistance. Multi-strand wire is better than solid wire. A strap is better than wire. No sharp bends, no coils of ground rod. Just stuff that in some respects is common sense, but it's not necessarily until you really think about it. The inductive reactance comparisons at 10 meg, 5 foot length. And now when we look at this, think in terms of, we're talking about this impedance, but we're talking about 20,000 volts. So suddenly we have a voltage drop across here that actually adds up to something. So if you have number 12 wire as your grounding conductor, 5 foot of that has 10 ohms reactance. You change that to 3/1000ths of an inch thick flat strap, and you're down to 1/10 of an ohm for 5 foot. So you're 100 times better just using the flat strap than you are, because it's all about the surface area. As far as the tower itself, guy wire should be grounded at their earth end, bypassing the turnbuckles and that kind of stuff. Insert multiple ground rods, even potentially, depending on how carried away you want to get, at where the guy wires come to Earth, you can even put radios from those points out. Again, always thinking about dissipation. I'm trying to dissipate this charge into the ground as far away as possible, as quickly as possible. And again, your ground will get saturated. So the more you spread it out, the better off you are. So just some of the numbers we're talking about here. Theoretical 150-foot tower, 40 microhenries of inductance. We're looking at a peak voltage across the tower of 360 kilovolts. Okay, 360 kilovolts. That's across the tower, but that still is creating some wild and crazy voltages that you're going to have to deal with. Or your equipment will by letting smoke out. So our management of this peak voltage is what determines the survivability. Another thing to keep in mind is there is a certain amount of protection that the tower provides to items that are around it. By that protection, that means not that they can't be hurt. That means that they will probably never get struck with a direct strike of lightning. And there's a 96% chance that that area right in there will never get struck directly. It'll be in the effective field of anything that happens, but it's not going to take a direct hit. So they kind of call that the rolling ball theory. You can take a 150-foot rolling ball and roll it across the ground, up and over anything you see, etc. And anything within this arch will always be in a protected area. Now, if your tower is over 150 foot tall, then suddenly you've got stuff up here, let's say side mount antennas, that are not in the protected zone. A 2-meter antenna sticking off the side down here, it's protected. But if it's up above the 150-foot range, it's not. So, and of course, the guy wires can change the geometry of where this ball rolls, etc. But the side mount antennas and that kind of stuff that are higher up can be protected by, let's say, horizontal lightning rods coming out, so that when the ball rolls up the tower, it's actually going to roll outside of those antennas, and they will again be in that 96% protection zone. Really, that's not anything any of us are probably going to ever have to worry about. It's just an interesting side note to all of this. Coax mitigation. Now we're getting to be I don't know, any of you that have done anything with coax know what a velocity factor is. Basically the speed of the radio wave through the coax. And this, all of a sudden, this becomes very apparent that we're working with RF. First of all, you want to ground the shield of your coax at the top of the tower and at the bottom of the tower. Again, when it comes into the building. And all of this that we're talking about is ideal case. Okay, ideal case. If you don't do it, that doesn't mean that everything has gone to hell in a handbasket. It just means it's not ideal. So this is just something to strive for, again, keeping in mind costs, etc. If the tower is over 70 feet tall, 75 feet tall or so, you have to start keeping in mind the fact that the coax coming down the outside of the tower, the shield of that coax, has a different velocity factor than the tower. The tower's like this big, the coax is like this big. And so after roughly 75 foot, there's enough of a phase difference that there's enough of a voltage difference now that you're going to boom, have an arc go through the side of your coax. May not notice it for a day or two or a month or two or even for a year until enough moisture goes through that pinhole to affect your coax. So it's more a term of, doesn't do a whole lot necessarily with lightning mitigation. That's just saving your equipment with the coax being part of your equipment. So they always recommend that every 75 foot on a taller tower that your coax shield be grounded. And again, it's nothing most of us are going to ever have to worry about. But again, it's just another interesting thing to keep in mind, because the speed at which this pulse is coming through your system varies on what it's writing, the tower or the coax. Okay, coax leaving the base of a tower. Ideally, you come down to ground level and you go across into the building. Underground, even a little bit better. Why is that? Well, again, this tower is a big voltage divider if you want to look at it that way. And example, again, with that 150-foot tower, if you come off the tower at 7.5 feet, you still have a voltage differential between that point and ground of 28 kilovolts. Something you're going to have to manage later. So why not just remove it by coming down to the ground and across? At 15 foot, it's going to be 90 kilovolts that you are going to have to manage later. So just come down to the ground and across and get rid of that little problem. Bulkhead. Oh man, you can spend all kinds of money at this point. Oh, can you spend all kinds of money at this point? A bulkhead. What is a bulkhead? A bulkhead is a copper plate with holes drilled in it, and your coax connectors, your SO239s, are built into this copper plate. And then also your lightning protectors may be built into this copper plate. And pretty soon you've got $1,000 wrapped up and no equipment hooked up to it, just getting that bulkhead in place. So that gets to be a really pricey part when you get into a professional installation or a commercial installation. That's still something to keep in mind. You should be aware of what a bulkhead is. You can kind of emulate it to a certain extent. Might not be as perfect, but it's better than nothing. And like everything else that we're talking about, a little bit is better than nothing. So let's see. Okay. Oh, we also mentioned here about the solid bond strap has more surface area circumference, actually with less copper by weight than a big chunk of wire. So, and the bulkhead is always grounded. Again, should be I have a bulkhead that I seldom use anymore, just for a whole lot of reasons. But it had, I think 4-inch strap. I think I had coming from it down to the ground, ring ground. Yeah, the pulse energy. Here's the deal with coax. Again, velocity factor of the outside of the coax is different than the center conductor of the coax. So at some point, you're getting enough of a phase difference between that pulse coming down the center conductor and the outer conductor that, boom, again, you're going to arc across. And really, that is what your lightning protectors that we all think about, that's what they're designed to do, is get rid of that voltage differential between the center conductor and the shield. And they do that in a lot of different ways. Where were we? Yeah, okay. One of the problems with lightning protectors, and with lightning protectors, you get what you pay for. I mean, a $20 one is better than nothing. $100 one's better than a $20 one. And again, we're back to how much money do you want to spend? But basically, if you get, let's say the ones that Polyphaser makes that are not cheap, but the ones that are in the VHF or up into the gigahertz range, this is kind of what they look like. And what you have here is a quarter wave stub at the frequency which you are using, which means that's high impedance. It's effectively not there. But at any other frequency, including 10 meg, it's a dead short to ground. There is no time involved. We're not waiting for the air in an air gap to have enough voltage to ionize. We're not waiting for a gas discharge tube to build up enough voltage to discharge. This is instantaneous. I mean, that pulse comes down from the lightning and it goes directly to ground. Just boom. I mean, there's no wait for anything. Of course, these are a little bit more expensive than some of the others. You probably won't find these for $20. So it's an interesting concept. And then, of course, they have the DC blocking capacitor in there, which does, if any of you use what's commonly referred to as a bias T, where you put DC on your coax, quite often to operate a remote tuner. In the weak signal world, they'll have RF amplifiers up on the tower or something that are powered that way. This pretty much eliminates the use of something like that. You're not going to get DC through this thing, and as soon as you stick your bias T on the wrong side of this, so you can get DC, you've just bypassed all of this. So it's whereas this is the ideal, it limits what you can do. This is another one where we have a tuned circuit here of some type that again has somewhat the same effect. You don't have to wait for a discharge across a gap someplace, before you provide a path to the Earth. Okay, in your station, all grounding should go to a single point. Don't take the easy way and ground this to this to this to this to ground. You're just creating even more opportunities to blow up even more stuff when you do that. So everything should go to a common point. That single point of ground should also have a single point to the larger grounding system, which may or may not be a ring ground outside your building. That's an ideal situation where you have a ring of wire around the building, sometimes referred to as a halo ground, although that's also one inside the building at the roof level, radials and that kind of stuff. Everything wants to go to that single point for the station, and that single point goes to the grounding system. And the more you can do that, the better off you are going to be. Okay, this is kind of a graphic of an ideal system for lightning mitigation. You notice all the radials that you have coming out, all the ground rods on these radials. Again, the concept is take this energy, move it out, move it away as quickly as possible. Do not give it time to saturate the earth. Do not give it time to saturate each individual ground rod in the wire. Get it out of here. They also have a ring ground around the building. So, and I mean, that's kind of showing how it's supposed to happen. So when a lightning strike does occur, this is kind of a demonstration of how the field is going to move away from the tower, assuming the tower is what was struck. So we've got this whole area maybe sitting at 40,000 volts, or make up any number you want. The thing is, the whole area is. Everything is coming up together as quickly, as close as possible, and going back down together. And that's the important part about all of this. So there are a few myths around all of this, and that is that an ungrounded tower is less likely to experience a strike. It's kind of true. I don't know if you remember, I haven't seen them so much lately, these brushes, these balls of brushes that they would sell to put on your tower. They may have a purpose, but not for what they cost. We'll get into that just a little bit. It's kind of funny that I don't know, you probably all know Florida is the kind of the epicenter of lightning in this country. So the company that makes these brushes somehow got a deal going that they would demonstrate how good the brushes were. So Miami International Airport has these things all over. And if you ever fly through there while you're taking the little train, look out the window. And you may not have noticed them. I did because I was looking for them, and they're everywhere. These little prickly balls about this big, you know. And Polyphaser has a movie that was taken, and it showed that those things were attracting lightning like crazy. Oh my goodness. I mean, they were all getting hit, just constant, you know. So again, you are going to get hit, and what you do with it after it hits. But the thing is, they do not prevent lightning from happening. That's, you know, which is how they are marketed. So another thing is that some people get the idea of, well, I've got this tower and it's got joints in it, and how about if I just run a copper wire down the tower leg, and that'll give me a good path to ground? Well, no, that's a myth actually too. So the ungrounded tower thing, it may be less likely to be hit, but when it is, and Polyphaser makes a big deal of never use the word if when it comes to lightning. You always use the term when, not if it occurs. It will. It's when it occurs. So when it occurs, if it is hit, you have no controlled path. You have done nothing to mitigate the effects of that pulse. And so the most likely path is whatever's hooked to that tower, which is, of course, your equipment, and it will be gone. So, you know, doing the tower correctly, at least you are putting some control over what is going to happen. The down conductor, again, we get back into the inductive reactance. The tower is a large diameter conductor. Might have a few high joints in it from a DC perspective, but from an AC perspective, from an RF perspective, it's a whole lot better conductor than that number 12 wire coming down the side. So the wire is effectively not even there. Plus the fact that so what are you going to do with that wire when you take it down? If you run it to a single ground rod, that is going to be saturated immediately and no longer conduct anything into the earth anyway. So an interesting thing about this is that the brushes do give off ions, but you'd probably have to have hurricane force winds to move those ions fast enough to actually do any good from that perspective. So it's not that the brushes are bad, they are not going to protect anything. Just like your lightning rod with a point on the top. That point, it's only one point. These little brushes have maybe 1,000 points. It's still not enough to move the ions quick enough to do any protecting. So from that perspective, they don't do much. This is the actual lightning machine that they use at Polyphaser. So if you are designing some equipment and you want to know how it will withstand lightning, you can go hire this machine, and you'll mount your equipment on this tower section here, which is suspended above the machine. And you can now run all the tests you want. And this is a big bank of capacitors, big capacitors, and they're all in parallel until they get charged. And then when you push the button, they go into series and kabang. And it's a big kabang. Yeah, let's see, yeah. I didn't know, I forgot that was there. I'm going to jump ahead just a moment here. Okay. There was a company that decided that when they were on a tall building, let's say a grain elevator, as we would know it around here, but any tall building, the best grounding they could probably do would be to run some 4/0 copper down the side of the building. They figured that'd be a good lightning protection. That's the best you can get. So they came in and they hired the machine. They ran 400 feet of 4/0 copper through the factory and the warehouse, suspended between earth and sky from the ceiling. and then they grounded it at the far end. And then they pushed the button. Well, this was about 5:30, 6 o'clock in the evening. Most of the people were out of the plant. A few office workers were still there when they were jolted when the whole building shook and there was an explosion. Well, it turns out that the concrete that this machine sits on had lower reactance than 400 foot of 4-aught wire. And the floor exploded, the concrete floor, between this machine and one of the beams, support beams of the building. And just gone. But that was the low inductance path. It was a perfect demonstration about how a big chunk of wire isn't going to do you much good when it gets to be long. So that was quite interesting. Resources that you can go look at. And some of these are very technical. Some are just kind of like what we've done here, kind of imparting some common sense. These are on the Polyphaser website. I just checked there again today because I knew they used to have a few. They've got a whole lot of them there now. Pages and pages and pages of white papers. I just grabbed a few here that looked interesting. That are very good documents. They might only be a page or two long. But all kinds of topics. If you want to really dig into this or any subcategory of lightning mitigation. Products you can buy. Again, the best protection is not the cheapest, but the cheapest is better than nothing. So again, you kind of have to get a feel of the whole thing and decide how much money you want to spend. I guess a rule of thumb is to look, doggone it, is to, let's see here. Oh man, rule of thumb is to use for a DC blocking lightning protector is probably one of the first things you should look for if you're looking for lightning protectors. And then from there, again, another thing is to invest in copper strap. It's not cheap, but it goes a long ways. And it's pretty easy to handle. I don't even know what rolls, size rolls they sell it in today. I didn't think to look at that. I know I've got some rolls that are about that big, and there's a whole lot of feet on them. And it's a good thing to have around. Now you can make your own strap after a fashion. For example, coax shield, old coax that you're going to throw away. Strip the shield out of it, flatten it. And it's not as good as solid copper strap, but it's a whole lot better than a chunk of number 12 wire. So it's something you're probably going to throw away anyway that you can save, crimp ends on it, whatever, and make your own flat strap. Again, things just to keep in mind, avoid coils to store excess anything. It's better to take that excess coax and kind of go back and forth than roll it up in a coil. Doesn't cost anything. You just do it a little bit differently. Never daisy chain your ground leads between devices. And again, the solid wire should be your last choice. Stranded wire is better than solid wire. A flat coax braid is better than any wire. So in summary, always think in terms of RF. Don't try to make a low resistance path. It doesn't matter. Make a low reactance path, the ground. Try to think about all voltages rising and falling together. I know it can be kind of hard to imagine, but there are some things that become obvious to you that it's not going to happen. And that's what we're after. The voltage itself is not the killer. It's the differential. It's the fact that everything does not come up and go down at the same time. That's the killer. So minimize the causes of differentials. And then again, there is going to be a huge charge and you want to get rid of it as fast as you can and as far away as you can. There we go. How's that? We're done.
Any questions for Chuck? before we let him get away.
Yes, sir.
Could you comment on second floor grounding?
Oh. Strap.
Yeah.
And you can buy strap up to 6 inches wide or better, but, there's something called, and it depends, this may or may not apply, probably does not, but something else that I didn't mention here, there's something called a Ufer ground. And that's actually named after the guy that invented the concept. If you were on that 200-foot tall building, for example, that grain elevator, what do you do? Well, just ground to the concrete. The mass of the building, if you will, becomes a huge capacitor to absorb that charge. So it's kind of like the concrete floor blowing up at Polyphaser, okay? It was the lowest inductance path to ground based on what was happening at that point in time. So it's not an insulator. It's just the mass itself. So a second floor, again, just keeping in mind, low reactance and whatever you can do, the best you can do. There's no perfect answer. So, I mean, that would be an ideal place to have a, if that's where you needed to be and you had a single point of ground there, to have a piece of any strap. I mean, even the 1 inch by 3,000 strap is better than a chunk of wire, going to ground.
I know MFJ had a product they called an artificial ground, which would basically
That was
tune the reactance between the
Right.
ground and the second floor.
and that was more for the RF ground perspective.
Right.
What I used to do, I used to travel all the time, and I could be on the 20th floor of the downtown Westin in Denver and want to get on HF. My artificial ground was a quarter wave of wire laying on the floor. And it worked wonderfully. I've done that many, many times. Hook it up to the ground connector of your tuner and off you go. So it's just a counterpoise. But again, it had nothing to do with lightning, but it had to do with the RF efficiency of the station, if you will. So, yeah, and that's what that MFJ product. I mean, I thought that was pretty smart on their part. There's a lot of things they come out with. I think that somebody was thinking, and that was one of them. I mean, it has maybe a limited use, but for when you can use it, it's a pretty good thing, Yeah. But that one had nothing to do with lightning mitigation or anything like that. So. Yes, sir.
Just kind of Simon Newham, I haven't really gotten antenna up or anything, but if I did, it'd probably be a dipole or something. And then I had this example from about 2001 or 2002. My family and I just come back from a trip. It's a clear July 4th night. We just plugged in our computers. We're checking our email and kaboom. And in our backyard somewhere, there was a lightning strike. The cable tuner was brown on the side. All the Ethernet cards that were connected were gone. And, the way it looked, I had it hooked up to cable network. So in our backyard, probably at least 360 feet of connector that was on a power pole, a real power pole. And then my cable went from 15 feet up into the ground and probably went at least 120 feet to my house. So that sounds like an example of phase differential, like you're talking.
Yeah.
By the time it reached my cable modem, it was probably really interesting.
Yeah.
So would I have, if I was a ham and I had something mounted on my wooden post, would I have wanted to get all kinds of grounds around that thing in my backyard, or?
Again, that's an ideal situation. Yeah. I mean, that would be the ideal if you wanted at that post out there, whatever you wanted the maximum protection. Again, you want to mitigate that charge. You want to move it away as quickly and as far as possible.
As near as I can tell, mine went from about 15 feet up, straight into the ground with no mitigation.
Yeah.
And the first mitigation was my cable modem, which was
Yeah.
smoke.
Well, I mean, that gets into, there's also protection that you can put on wires. There's protection you can put in your AC system. There's all kinds of lightning. I only covered the part that would impact antennas and antenna systems.
How about you swung an infant antenna up between two trees and you ran your coax down?
Yeah. The odds of that antenna being hit are nil.
Yeah.
Of the antenna itself being But in that case, what you're concerned about is something around you being hit, and everything that you're sitting on is going to go up. I mean, the ground you're standing on, the voltage is going to rise 10, 15,000 volts. You just want everything to go up with it and come down with it, you know. In the AC world, AC power world, they have something called ground fault, where suddenly the ground you're standing on is no longer ground. And it might be 10 or 15,000 volts different than ground. And meanwhile, that drill, that electric drill with a metal case that you're hanging on to, it's looking at a different ground. And suddenly your foot to your hand is 10 or 15,000 volts, hence ground fault outlets and that type of thing. Right, you know, and break that circuit. But
They took back.
the Allman Towers, 2,000 foot, I'm 10 miles from there. I've watched them get hit, and I don't mean just get hit. I remember one night I almost set up my camera on time lapse because I stood there and I swear it was 3 or 4 seconds. 2 huge bolts came down and just. I'm going. I mean, if you're watching the TV, they don't even blink. I've been in the building in a storm. I don't know what protection they have, but it gets really noisy inside that building. There are contactors going bang, 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 bang all the time. But yet, if you're watching the TV, you don't see anything happening. I have no idea what they use, but they just, it's to them, it's all mitigation. We are going to get hit. We're going to get hit regularly. We're going to get hit multiple times. How do we dissipate it? And, you know, that right there, the engineering around that would be very interesting. Because if we would take that and miniaturize it for your station at home, you'd be pretty secure. But Skip.
Chuck, you used the term saturation several times. What gets saturated and what is doing the saturating?
The pulse itself, there's 2 things that'll get saturated. Let's say we looked at those radials back there, depending on what the wire's made of, it's going to only handle so much current, okay? And at some point, it's going to get saturated. You're going to have a reverse reactance on it. In other words, it's basically going to shut down. It's not going to move any more current. The same way with that ground rod. I think something I didn't state, but I think it's stated in there. Another thing with the ground rod, a 10-foot ground rod, by the time that pulse gets to the end of that ground rod, the ground rod itself is saturated and has a counter force that basically won't allow any more current to come down. So the ground itself can only take so much charge until it's full, and that's saturation. So again, you want to transport that as far away as you can so that you don't try to saturate one little spot. That make any sense? Okay.
So the ground rod and the earth are, even though they're straight, they're starting to act as an inductor
Exactly.
to block the change of voltage.
Right. Yep. 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 Again, because of the magnitude of the pulse that we're talking about. It's just, I mean, what was it across the tower? 480 kilovolts or something. I mean, that's a whole lot of energy that we're trying to move. So, yeah.
Very highly conductive.
Yeah.
Ground rods that are not bonded together. If there can be a voltage differential between the 2 ground rods.
Yep.
So if you have a ground rod for the house and a ground rod for your entry box, what happens is the voltage differential is equalizing itself. And that equalization happens through your radio equipment, through the neutral wire, to the other thing. So
Yep.
that's another reason why you want to bond.
Yep. It's all about the differentials. The voltage rise and drop does not hurt anything as long as they all rise and drop together.
Let me check online here real quick and see if we've got any Questions online? Stop sharing here. Ron has a question. Go ahead, Ron.
Yeah, I was wondering about static charge buildup, like from wind across wires and antennas and stuff. And some of my lightning arresters have a little coil to ground that's supposed to bleed that off. Does that help with lightning protection at all, or is it just trying to keep the charge off the antenna?
I would think it would help with lightning protection too. Yeah. Because again, that coil has to be I mean, a coil is always related to a frequency in some manner, so it has to provide a high impedance path to the frequency that you're using going through that device, through that lightning
Right,
protector.
yeah.
But a low impedance. Now, on the other hand, that static charge is I don't know, there's not enough voltage there, and I don't know that it even has a rise and a fall time to make it truly RF. So the thing is, there's the same coil that impacts that I would think would help in the case of a lightning strike. Again, it won't fix anything.
Yeah,
but it would help.
I just wonder, with the static charge buildup, would that attract lightning? So you bleed it off so it's less likely to get hit?
Oh, no, I don't believe so.
Okay.
One way, just from experience, to get rid of that static buildup is to use a grounded antenna. So, I mean, if you're using a Yagi antenna, you have two choices. You have where all the elements are at ground at the same voltage as the boom, other than the driven element. And then you have others where everything is isolated. And even the driven element is grounded, if you're using a gamma match or something. So those antennas tend to be a lot quieter than antennas that don't use that method, just because they're able to discharge that snow static, what I call it, because that's when it happens a lot. You get decent winds and a lot of snow, and which is what you're going to hear on the antenna. Another thing is, any antenna that it's a loop, like a delta loop, any antenna like that, a folded dipole, even the old VHF Yagis that used the folded dipole driven element, those were all quiet compared to ones that aren't. So yeah, there's times that static you're talking about can be so bad. In my case, I have to switch to a terminated antenna, and just it all goes away. It's gone completely compared to other antennas. So, but the terminated antenna is a closed loop, so it just doesn't let it build up to start with. See?
Okay, yeah, thanks. That helps.
We got a question online here, Chuck. Do houses with no third ground prong on outlets have special considerations, like really important to ground chassis the common ground?
Oh, special considerations is to replace the wiring, I guess. It's oh my goodness.
From a lightning perspective, any information there? Because I would think that you're going to have differential now, no matter what.
Yeah, you're always going to have differential, and without the third wire, you've given up that much more control over it. And the only thing between again, your equipment's what's now in between. Yeah, the lack of that third wire is just it's never good from a lot of reasons, and it's definitely not going to aid, put it that way.
Any other questions? Awesome. Well, again, thank you, Chuck.